As a final example of applying Bernoulli's law, let's talk about the Venturi effect. So we imagine a flow where it's changing in the cross-sectional area of the flow. So let's say I have a pipe that's relatively small and it's opening up like this. So if I were to draw in some streamlines on this, they might kind of go like this. So the streamlines get farther apart in the larger part of the flow. And what we want to do is we're going to assume, let's say that these are our 2 points, 1 and 2, that they're at the same height, and we're interested in the difference in the pressure between them. So since y1 equals y2, Bernoulli's equation will simplify to P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. And so that means that, let's say, if V2 is less than V1, as shown in our example, that means that P2 has to be greater than P1. Remember that you can only apply Bernoulli's equation to 2 points that are on the same streamline. So I should have maybe drawn one, so there should be some streamline that contains both points 1 and 2. So people sometimes misinterpret the Venturi effect as saying wherever the velocity is higher, in our case 0.1, that means that the pressure is lower. That is true if the 2 points you're comparing are on the same streamline. So maybe we should write that out. If 2 points are on the same streamline and have the same y, then the point with higher velocity has lower pressure. And that's something that is really not at all obvious. So now I will show you a demonstration of this. All right, we're going to demonstrate the Venturi effect using this. So this is just a T here. So these 3 sides are connected together, and there's a little tube, copper tube connected to this end. And I'm just going to use this canned air to blow air through the tube. So it's going to go straight across. So the whole flow basically goes straight across. And as it's traveling in this part, it's traveling through a relatively small tube diameter. When it gets to the outside, it can expand. So you can think of that as being a larger tube diameter over here. So that means that the velocity, since the cross-sectional area is larger here, the velocity is lower than it is here. And the lower velocity means that the pressure is higher, or another way of saying that is the higher velocity here means lower pressure. We know the pressure here is atmospheric pressure, so this is below atmospheric pressure, so it's going to suck air in through this tube because we're at less than atmospheric pressure. And I'm going to see if I can use that to pick up this little piece of paper. So there, I've got it. I'll let it go. Try it again. Pick it up. Let it go. So it really works.